This question is about finding what we will learn to be a regular conditional probability in the case that we have two random variables that are jointly continuous. So in particular, the variable x that we're taking the expectation of and the variable y that we're conditioning on are jointly continuous. In this case, we take the marginal fy by integrating out x, and then we form the conditional density fx given y as the joint over the marginal in y. And we do that for all x and y such that the density for y is greater than 0. We have to suppose that the expectation of x, the normal expectation of x, exists, meaning the expectation of the absolute value is finite. And then we are to show that the conditional expectation of x given the sigma algebra generated by y is the integral of x with respect to this conditional density. So to show this, we have to show that this expression, the integral of x with the conditional density, satisfies the properties of conditional expectation. And the first one is that of sigma y measurability. The joint density was measurable in both x and y. The marginal with respect to y is measurable with y by Fabini. So the ratio is measurable in xy, as is x times that ratio. At this point, then, we use Fabini's theorem to conclude that after integrating out the x, we have something that's measurable just in y. That's a part of Fabini's theorem. And so this means that if we substitute the random variable y in, this proposed conditional expectation, the integral of x, fx given y, of x given the random variable y, is sigma y measurable. Property B, the expectation of the absolute value is finite. And so the way we'll do that is to show the expectation of the absolute value of x given the conditional density at random variable y is less than or equal to the expectation of the absolute value of x, which we assumed was finite. And so we look at the left-hand side of what we want to show, the expectation of the absolute value of the integral of x times the conditional density at random variable y, and we use Jensen's inequality to bring that absolute value inside the Lebesgue integral dx. Then we have on the inside the integral of the absolute value of x with respect to the conditional density of x given y. And then to take care of the expectation, we rewrite that out in terms of the marginal for y, and we write that as the outer integral, the integral of the inner integral fy y dy. Moreover, the conditional density multiplied by the marginal in y just gives you the joint back by the way we define the conditional density. And now we apply Fabini's theorem to switch the order of integration, and so we can now integrate with respect to y first and then x on the outside. And so then we integrate out over the y, and we're left with the marginal in x, which we then integrate with respect to the absolute value of x to get the expected absolute value of x, which we know is finite. The last of the three properties that we need to show is taking out indicator unknowns. In particular, we need to show that the expectation of 1gy times the conditional expectation of x given sigma y is equal to the expectation of 1gy times x. And that has to be for any Borel set G. Okay, so to do this, let's look at the left-hand side, but substitute in the postulated conditional expectation, the integral of x with respect to the conditional density evaluated at the random variable y. So we have the expected value of the indicator of y times this integral of y. And we then use Fabini's to bring the expectation inside the integral. In other words, we can take the integral and the x outside of the expectation, and we're left with the integral of x times the expected value of 1gy times the conditional density at the random variable y. dx. And then we can substitute in the conditional density, which is the joint over the marginal in y, and then evaluate this expectation, which then replaces the instances of the random variable capital Y with a little y, and then multiplied by the marginal fy of little y, and then dy. So we just substitute in the formula and for both the expectation and for the conditional density. And then we can simplify. We can cancel out the fy's, and we're left with the double integral of x 1gy times the joint density in x and y dy dx. But this is exactly the expectation of x times 1gy, which is what we needed to show.